2 of 2. This is Rob Campbell sitting with Andy Detwiler, August 23rd, 2008. We're at the South Dakota School of Mines and Technology, and we're continuing our discussion about the T28 storm penetrating aircraft. Oh, so you were saying if you look at this Omaha museum, which accepted this T28 was a little bit different for them.
Well, what I'm saying is if they get something that needs restoration, or even preparation for exhibit, you can't just park a functioning airplane in a museum and have it drip oil.
Right.
They need money. Like I say, some of these projects are going to attract money from people who have money, but when you get something like a research aircraft that, the people who used it don't have pockets full of money to donate, they're kind of, how are they going to get it ready to exhibit?
Right.
It's going to, even though the airplane was free, it's still going to cost them money.
Sure.
Tens of thousands of dollars at least.
Really?
I would guess.
To prepare it.
To
You can't just
prepare
drain the oil, roll it all over on a...
Well, I'm not sure.
trailer?
I'm just guessing.
Okay.
But just based on what they say on their website about how much they need to restore some of these other airplanes.
I see.
They have a lot of volunteer labor too. I mean, aircraft people that just enjoy working with old airplanes.
Right.
Who volunteer their time. But if we could have donated the airplane and $25,000, I think things might have turned out differently.
And you know for a fact that there was a change in leadership there at the museum?
At least
one.
Within the year preceding the time the airplane was sold, I think there were at least 3 different ones.
Oh, really? And so how did IAS then hear that something had changed down there? That something had happened to the T28?
I think Julie had heard something.
I see. So they sold it?
Yeah, and we don't know, the details. Tom might know the most, Tom Warner, because he's been dealing with the guy who bought it.
He is the one who bought it. We know that he bought it from the museum.
Mark Clark. Right?
Yeah, there was not, somebody else didn't have it in the meantime.
No, and Mark Clark is kind of an airplane broker, restorer. He deals in so-called warbirds. So, his idea of getting the airplane is to basically, his plan, which he executed, was to what they call part it out, sell the pieces of it that are worth something and then scrap the rest.
Right. So you were there. You went to Mark Clark's place
Just
in
recently,
Illinois.
a couple weeks ago, yeah. I was traveling east to go visit family and managed to pass through Rockford where his operation is. And Tom had set it up for me to get together with him. I had a small pickup truck full of remaining T28 related parts and hardware that we still have here.
Right.
What Tom is working on with Clark is a deal to take the pieces that he hasn't parted out, basically the scrap that's left, and donate it to another museum and use those pieces to put together some sort of an exhibit. It might be a wing sticking out of a half of a fuselage or something like that.
So you have a bunch of digital photos?
Tom has a lot more. I have 3.
Oh, did Tom go with you?
No, he's been
visited.
exchanging photos with Mark Clark.
I see.
Clark is showing, this is what I've got, here's a picture of this, that, and the other thing.
So if I go there today, what do I see of the T28?
If you go to Clark's website.
Or if I just visited there, if I went today, if I drove there to look at the T28, what would I see?
Well, he's got it stuffed into a hangar.
It's in one piece?
No, the wings are off the fuselage. The landing gear has been sold, as far as I can tell. The engine has been sold, there's no engine on it.
Mhm.
So the fuselage with the canopy is sitting there, and the wings are kind of sitting alongside it. And there's a bunch of boxes and other things piled up around it.
Do the wings or fuselage have any commercial value, would you guess?
I would guess not, because, you know, they've been modified.
Would the FAA let somebody fly this plane? Do you know?
I doubt it.
Yeah. What kind of scrap value are we talking about?
Just, you know, however much aluminum is worth per pound.
Is that a lot of money to him?
I think he could probably make more money by donating it,
Oh.
actually. I mean, and taking a write-off.
So the stuff that's left is not the valuable parts?
No, see, yeah, we were worried that if somebody were to sell the airplane, some nut would buy it and go out and try to fly into a thunderstorm
Right.
without the kinds of support that we normally employ, you know, having somebody on the ground watching a radar and talking with a pilot about escape headings and different things. And so in a way, it's a good thing that Clark didn't keep the airplane
Intact.
and try to sell it as a unit. Now, one of the problems is with airplanes, you have to have like a maintenance record
Sure.
and regular inspections by qualified mechanics and all this other stuff. And you know, we operated that airplane under a restricted category. I mean, they have different ways you can operate airplanes.
Right.
Restricted means you basically do whatever you want to it and you're responsible. But you can't carry a passenger. I think that's what they call public use. If you have somebody in the airplane
That becomes public use.
other than the pilot. So once you've bored holes and bolted things onto this airplane for 30 years, there's no way the FAA is going to certify it for public use sort of thing. And so I guess somebody could have bought it and operated it as a restricted category, you know, as just fly it him or herself. I don't think there would be any problem with that.
So what Tom or other folks around here hope to do now is what? I mean, could you?
Well, and you can get details from Tom.
Sure.
But, I mean, we have a number of old pieces and spare parts and things sitting out at the WestJet.
And they have some value.
And they have some value to somebody like Clark, who might need them to restore a different airplane, or could sell them to somebody who's restoring T28s or whatever. And in fact, we have a complete propeller that could go on an airplane.
Mm-hmm.
And so Tom's idea is to trade all this remnant stuff to Clark, and then Clark will donate what we think is necessary for a museum display.
Did Clark seem receptive to this
Yeah.
kind of idea when you talked to him?
He wants to get that stuff out of his hangar because the only way he makes money is to restore airplanes and sell them.
I got to keep it moving.
Got to keep things moving, and renting space to store junk is not
Right.
going to make a profit for him. So.
And then that could still be a pretty decent exhibit if you got the fuselage, the wings,
That's Tom's hope. You could-
and a fake propeller on the front. What the heck?
Yeah, and in fact,
You don't need an engine especially.
Clark has offered to donate other spare parts of T28s,
Right.
that
Landing gear would probably be nice.
some non-functional parts that he
Sure,
can't,
sure,
don't
sure.
have any value to him. The problem is that the only likely museum is a museum that is just a paper organization at the moment in Norman. They want to have a National Weather Museum.
Hmm.
Because in Norman, where the National Severe Storms Lab is, they have a lot of old historic junk. The first weather Doppler radar and
Sure.
different pieces of research equipment that were first of their category. And they have a large atmospheric science community. There's a lot of storm chasers that go through Norman and pay homage to the Severe Storms Lab every spring. And so it's likely that a museum there would actually attract visitors, have interesting stuff. But they don't have a physical building or anything right at the moment.
Yeah, they
All
don't-
they have is a piece of paper saying we're a 401 or 503 or whatever, tax exempt organization, and
exist
you
as
can
paper.
donate us money if you want to.
And it'll sit outside for
And so
some period of time with a tarp over it.
there'll probably have to be some, get the stuff out of Clark's shop and move it someplace else into somebody's barn or something until something happens down in Norman.
Hmm.
But, you know, in the 90s, late 90s, this would have been a much easier task when people had more disposable income that they didn't know what to do with. I mean, hard economic times is
Yeah,
particularly tough on museums, I think.
I think so. So we sort of started in the middle of the story and went to the end. Can we back up and start? Could you, a few more questions about what you were doing in these operations. First of all, could you give me a little bit of your biography, where you came from, what your background was, how you came to be involved with IAS and the T28?
I did my graduate research at SUNY Albany, and I worked with a guy named Bernard Vonnegut on a project that did involve aircraft research. We used it's actually a powered glider that was used by, or developed by New Mexico Institute of Mining and Technology for thunderstorm research, and we were using it for high altitude sampling in cirrus clouds on my particular research project. So I had some experience in airborne research as a graduate student, and then I did, after graduation, getting my PhD in 1980, I stayed at Albany for about a year and a half because basically I couldn't find another job. It was the end of the Carter administration. That was the era of stagflation when interest rates were like 15, 16%, and the economy was not doing so well. So anyway, it was useful because I was able to finish up, as PhD students do, finish up things and get them published. And then I applied to the postdoc program at NCAR, and I went to NCAR in the fall of 1982, which was a year after this big project at Miles City, where they had been studying hailstorms in the summer of 1981. And they had tons and tons of data, and so all the postdocs that went into the division I was working in, which was at the time called the Convective Storms Division, were working on analysis of data from this project. And so even though I wasn't physically at the project when it was conducted, I worked on a lot of thunderstorm data, airborne thunderstorm, airborne observations in thunderstorms and radar observations and things like that while I was at NCAR. And then I kind of out of the blue got an offer to go work for GE aircraft engines in Cincinnati on a completely different problem, contrails, actually contrail suppression.
Military stuff.
Military stuff. And I worked there for 3 years, and then it became, I guess I could see that the project I was working on was going to wind down, and it wasn't obvious what else I would do at a jet engine plant. And as a meteorologist or an atmospheric scientist. So I started looking around, and while I was at GE, Paul Smith here at the School of Mines was in the process of lobbying and negotiating with NSF, along with some other university facility operators, saying, look, we can't maintain these radars or airplanes at our institutions, not knowing whether we're going to have a project next year or not. And, so NSF developed this program of cooperative agreements to support universities to maintain facilities that could be used by anybody.
This is the facility agreement.
And so Wyoming had a King Air aircraft. Colorado State University had a radar, research radar. And the School of Mines had the armored airplane. So when it became clear that these cooperative agreements were coming down the pipeline, one of the aspects of the cooperative agreement is the institution has to cost share. And normally what institutions cost share is people. So part of this cooperative agreement was that the institution would pay the salary, 6 months of salary per year for somebody to be a facility scientist, a person who would work with the users of the airplane on scientific issues.
To help them line up projects and proposals and...
Yeah, and negotiate how you're gonna mount these things on the airplane, and is this the right instrument for the science you wanna do?
I see.
You know, we don't have enough power for this instrument, but maybe this one will do the job for you, and, you know, work out all those issues. So they advertised a position, and I applied for it, and came here in the fall, February of 1987. And so for the beginning of the cooperative agreement era, if you want to call it that. And so during my original appointment was as a research scientist. I didn't teach, I just worked with users of the airplane.
And then NSF paid for the other 6 months of your salary?
No, the school would the school paid all my salary.
Oh, I see. And
But 6 months of it counted as cost sharing.
I see. Because 50% of your time was as this facility research scientist.
And then the rest of my time was working on other projects that
You do
had
whatever.
different sources of funding.
But you weren't teaching at the time.
And after a couple of years, they worked me into the teaching rotation, and so part of my time was covered by teaching.
So, did you right away start doing summer field projects?
Yeah, in fact, in 1987, we had a project in June. I'd only been here a couple of months.
And is that part of your NSF duties then? Or is that the other 6 months?
No, that would be, well, you know, I would have to go on any project that the airplane was involved in.
Because you're the
We got
research-
extra money to do these so-called deployments.
Sure.
Above what the cooperative agreement normally included. So my duties were somewhat ill-defined at the time because they really had another fellow, Dennis Mussel, who was basically the facility scientist.
But not officially.
So,
And so at the time, Muscle had been, I mean, I think of you as the radar guy.
and he
Sitting on-
was the radar
He was,
guy.
right. And then eventually
He would sit
you.
at the radar.
You eventually did what Muscle had been doing at the
Because he
deployments.
retired in the early 90s, right?
Oh, I see. So for a few years you were still hanging around. So you immediately started going on deployments in June of '87. What did you do when you were there?
Well, I worked mainly on working with the software engineer, Ken Hartman, to kind of beef up our local software. See, up until that time, most of the projects on which the T28 was involved NCAR. And NCAR actually handled most of the data. And we wanted to develop our own data software and data analysis tools and things like that. So Ken and I worked for several years trying to beef up our capabilities here on campus.
So you mean going all the way back to '72 in those years, the data would go to NCAR on the tapes, run through their computers, and, well, you were doing that as a postdoc, right, at NCAR?
Yeah, there was T28 data. I didn't actually use any of it.
Although, School of Mines, is it true that IAS people were analyzing those
Well,
data?
they were, but some of the instruments they had recorded in a form that was actually on, they actually had 2 data recording systems on the airplane. NCAR handled one and the School of Mines handled the other.
I see.
And so there was a lot of cooperation, but then once this facility operation was implemented, the idea was we'd be self-sufficient and we could work directly with the users, and NCAR
Sure.
wouldn't have to be involved because they didn't have time. I mean, people there didn't have time. So that was, and I worked a lot on writing papers. I mean, that's the game in science. If you do these projects, it's important to get publications out to show that what you've observed is useful.
Sure.
So I was an extra writer. And then Dennis retired in 91 or 92, although he still came out to our projects at least, I think 96 was the last year he actually did the radar work.
Mm-hmm.
So
So he was working for a few years just at the deployments.
just on the deployments.
And so then when he retired, you started being the radar guy too?
Right.
And so you would direct the plane saying, here, okay, it's good to go here, here's your heading, here's your...
Right.
So you were the one who was mostly, the radar guy is the guy who was most talking to the pilot. It's basically a conversation between you and
Yeah,
Charlie.
you're trying to help them get it into the interesting parts of the storm for whatever science you're trying to do, but do it in a way that isn't going to cause serious damage to the airplane, so,
Sure.
or to the pilot. So, and it's a learning process because you can't tell from a radar exactly what's going on in a storm. It's and Dennis trained me, and then I did my best, but I have to confess that sometimes the airplane got into places they probably shouldn't have, based on the number of dents on some of the instruments and the wingtips when they came down.
You got him a little too thick, huh? On occasion.
Yeah, well, it's, you know, the aircraft, or the radar is sweeping through the storm in a sequence of scans, and you have to kind of build up this three-dimensional image of
In your head.
in your head. And I think Dennis had been doing it from, well, he started in Henry, so
Yeah, a long time.
he did it about 20 years. I did it for about 7 or 8.
Mhm. So this is a question I've asked a lot of people then, and maybe you've answered this already. But over the time you were around, and that's 20 years ago now, 15 years maybe while it was operational, how did you see the whole program mission T28 thing change?
Well, I mean, technology let us do more from year to year. You could store more information on board. I mean, when I started, they were recording on 7-inch reel, 9-track tapes. And I think the capacity of one of those tapes is like 5 megabytes. So you were limited because you can't change tapes during a flight. Pilot can't do that. So you were limited in what you could record, and we eventually added PCs with hard drives and recorded directly on, well, first time we had a PC, we used a cartridge tape that could store like 40 megabytes. That was 1988 or 9 we added that. And then around 1998 we added a PC that could store a gigabyte, you know. So, you know, capability increased instrument-wise, but you know, you're still limited by where the airplane performance as to what parts of storms you can get into. And the interest, one thing I brought into the program was an interest in atmospheric electricity. They really hadn't done much of that in the early years. The focus was on hail. And maybe you've talked to Paul or to Dick. I mean, they did the hail research experiment in northern Colorado. Did a couple of seasons, well, one full season and a truncated season due to the accident on the runway in Norman and hailstorms in Norman. I've forgotten the year they went to Switzerland.
Was that before your time?
Before my time, 82 maybe,
Yeah.
83. So they spent 2 seasons in Switzerland. Then they went to Alberta in 1985. Again, the Swiss experiment, they were actually trying to verify whether seeding reduced hail from thunderstorms. And same thing in Alberta. So maybe from 1972 to 1985, the focus was on hail. And then when I started, we started the projects we were involved in were basically looking at the periphery of hailstorms, or the early phases of hailstorms, and doing what they call tracer experiments, where you have a source of sulfur hexafluoride, an artificial gas that's not normally present in detectable concentrations in the atmosphere, and you have an airplane that flies around and it's pretending it's basically seeding the storm with this gas, and then you have detectors on other airplanes trying to find out where this gas is going, and the object is to verify that if you were dispersing seeding material, that it would be getting to the parts of the storm where it would be doing some good.
I see.
And so we did that kind of work in 87, 89, and 93. But starting in 89, we added instrumentation to monitor electric fields around the airplane, which tells you something about how thunderstorms are charging up. And from 89 through, basically through steps in 2000, we continually improved our capabilities for doing that. And then in 2001, John Helston had been involved in some modeling of ozone and nitric oxides in thunderstorms, how precursors get into storms, what reactions occur in the storms, how much of the stuff gets lofted into the upper atmosphere out of the top of the storms. And he wanted to get some measurements. And this kind of ties in with atmospheric electricity, because lightning discharges create oxides of nitrogen. So we found a commercial NOx analyzer that really wasn't designed to be used on an airplane, but we got some help from some people at the University of Colorado, and we were able to demonstrate, we couldn't measure to such low concentrations as the state-of-the-art instrumentation, but lightning makes such high concentrations anyway that we thought we could still do some good. And in fact, John, we collected data as late as 2003 on that, but we haven't had a grant really to put a student on analyzing the data. So that's, John is still seeking funding for analysis of that data. So, airplane in my tenure kind of phased from observing hail growth regions to what they would call hail embryo regions, where the precursors of hail develop, using these tracer experiments. And then into atmospheric electricity, we did experiments in Florida and Oklahoma, North Dakota, New Mexico, where electricity was part of the goal. And kind of throughout that, starting in the early 80s before my time and continuing up as late as 2003, one of the goals that periodically we were involved with was to collect information just on what types of hydrometeors are present in different parts of storms, compare that to the signatures from these polarimetric radars.
And that's the kind of work that they've been doing way back, right?
I think 1984 might have been the first time the T28 was involved.
Is this Ted Cannon's instrument?
Well,
or was that earlier?
Well, Ted Cannon's instrument flew in the Hail Research Experiment. We flew it again in 1991 in Florida.
Same instrument.
Same instrument. But in the early 80s, it would be, NCAR developed a radar that was broadcasting pulses that were alternatingly polarized vertically and horizontally. That's what they call a polarimetric radar. And then you can look at various signatures, various combinations. You look at what gets reflected back. And different shaped particles reflect the different polarizations differently.
Sure.
So you get some idea of whether they're raindrops or hailstones or snowflakes.
And so T28 went in to get sort of ground truth data for that. For
And,
in situ data to
in
compare
situ
to the
data,
radar.
and I think the first field experiment was Maypole in 1984, in which they actually flew where the NCAR polarimetric radar was scanning.
Mhm.
And almost every project, well, not every project, but many years subsequent to that, most of our projects had polarimetric radars, and so our data could be used to verify what types of particles were present in different parts of storms. And if you look in the most recent text on polarimetric radar is written by a couple of professors from Colorado State, and it's just full of image printouts from our probes, because it was, at least as far as convective storms go, it was the main source of that type of information.
This is not an important question. When you were sitting on the ground and looking at the radar, is this the kind of radar, could you see the T28 on the radar?
Yeah, we always...
Was it a blip on the radar?
Always, well, we
Or was it
didn't...
a different kind of radar?
The radar doesn't detect the airplane directly. Well, it does if the radar beam happens to hit the airplane,
Oh.
but it's only going to hit the airplane sporadically.
Oh.
So we always had a system where we would get the aircraft position another way and plot it on top, continuously on top of the radar,
On the
even
same
if the
screen.
radar wasn't looking right at that instant at the airplane.
I see. So you, looking at the screen,
I knew
were you,
where the
were you
airplane
literally
was.
looking at like a green screen with the line going around,
No,
or
these
different
are
kind of?
like colored computer screens.
Oh, so it's fancier than that.
And the radar reflectivity is color-coded.
I see. This is maybe a more important question. By the time you came in '87, let's say, or maybe even by the time you were a graduate student, was weather modification a major issue?
Well, it's funny, if you look at my generation, I mean, well, going way back, if you go back to the 50s, there was the initial surge in interest in weather modification. There were almost no academic programs in meteorology in the country that had the expertise. Well, there were very few total. I think NYU, Chicago, one of the California schools, UCLA maybe,
Had meteorology programs?
had formal meteorology programs. And so they had two things happen in the 50s. One is the weather modification scare. I mean, can you really dramatically change precipitation by cloud seeding? Nobody really knew.
Call it a scare?
Well, I would call it a scare.
What do you mean by that?
Well, there was a lot of debate. Some people said, well, sure, we can make it double the rainfall or whatever. And
Okay.
other people would say, no, nature's too messy. Just dispersing a little bit of silver iodide smoke's not going to make much difference. I mean, you had people, in fact, one of the early, in the lab where modern cloud seeding techniques were developed, at GE, as a matter of fact, they were doing some experiments on aircraft icing in the 40s during the war, and they wanted to, it's kind of like Ice 9 in Kurt Vonnegut's book, Cat's Cradle. Have you ever read that? No. Well, anyway, if you could freeze, you get aircraft icing from supercooled water.
Right.
So if you freeze the water and make it ice, it's not going to freeze onto the airplane, make it into snow.
Right.
And they'd also been doing some P-static experiments, because when you fly airplanes through snow, you charge up the airplane, it starts to discharge, and it interrupts your radio communications and makes fighting wars more difficult. So GE had been doing these studies of clouds, basically, on top of Mount Washington.
Way back.
Way back, during the war. And after the war, I think they were still looking at these sorts of problems, and Vonnegut had an interest in nucleation, how you change one phase to another. And
Kurt Vonnegut did.
Bernard Vonnegut, Kurt's older brother.
Oh.
So anyway, in Irving Langmuir ran this group. Vonnegut worked for Langmuir, and this other guy, Vince Schaefer, who was basically just a machine technician, Schaefer was building a cloud box where they could make a cloud in a supercooled cloud in a laboratory to do experiments. And he was trying to cool one of these boxes down one day, and he put in a chunk of dry ice, and he found out that the whole cloud turned to ice. I mean, ice crystals. And so he did some experiments flying through supercooled clouds in an airplane, throwing out dry ice pellets, and he could turn the clouds from supercooled droplets to snow.
And the snow fell down on the ground?
And snow falls down on the ground. And about the same time, Vonnegut had the idea that you could fool supercooled water by introducing silver iodide, because silver iodide looks like ice. It has the same, roughly the same crystal structure.
Oh, that's why it's silver iodide. Iodide with a D at the end.
Yeah, and he said, and so he had these, Schaefer had made these boxes that you could make clouds in, so Vonnegut put some silver iodide smoke into a supercooled cloud in a box and turned it to ice. And
Did you say smoke?
Smoke, yeah.
You burn it and it makes...
You vaporize it basically
Vaporize it.
in a flame, and then it recondenses into little tiny particles.
And then you throw them out of the plane.
Well, you don't, you burn them. You have a burner on the airplane.
plane,
It's
right.
burning a solution that's got silver iodide
Okay.
in it, and the smoke is going out behind the airplane.
I see.
So anyway, this was pretty dramatic, and so commercial cloud seeders appeared and said, we'll make it rain for you, and we'll, by dropping dry ice into the cloud, or that's fairly expensive. The nice thing about silver iodide is you can put like a furnace burner that burns propane, say, out and feed a solution that's got silver iodide into it, and the stuff goes up into the air and into the cloud. And cheap. And Irving Langmuir set up an experiment where he ran a burner on top of a mountain in New Mexico, randomly, and looked for changes in rainfall on the East Coast. And he claimed there was a correlation that, if he ran his burner in New Mexico on Tuesday, it rained more in the East Coast on Thursday. I mean, this is the kind of stuff people thought was within the realm of believability.
Do you think that's within the realm?
I mean, it wasn't, and it just drove the Weather Bureau, was what they called them back then, nuts.
National Weather Service.
What is now
Right.
the National Weather Service.
Why did it drive them nuts?
Because they said, well, meteorology is way too complicated, and
Oh, they said you're crazy.
dispersing a few pounds of smoke into the air in New Mexico is not going to change the rainfall in Philadelphia 2 days later. But there was a dearth of qualified scientists to really look into these things.
Sure.
And so NSF, well, no, I take that back. Congress, there's an article in the bulletin at AMS that details the history, but there was a blue ribbon panel convened. In fact, Harry Orville's father, was on it, to say, how are we going to grow expertise in atmospheric science? And it turned out that the recommendation was NSF should be the agency. And so the NSF set up a program of research in atmospheric science, and just about anybody who sent in a proposal was funded. And they started to grow academic programs.
So the gold rush was on.
And through the 60s, there was a lot of research on weather modification. Into the 70s, the National Hail Research Experiment, but then at the end of the 70s, everything shut off. And I think the Institute of Atmospheric Science was started as part of that here. It didn't get its funding from NSF originally. It came through the Bureau of Reclamation. But, they were just, it wasn't really known how powerful these cloud seeding techniques were, and experiments were done. Schleissner was one of the big early players. And, there was kind of Cold War got into it because the Russians would say we can suppress hail completely. And in fact, the National Hail Research Experiment was set up to test a Russian scheme.
Right, the big drop zone.
Big drops.
And that was T28's debut.
And that was what led to the NSF funding McCready and Schleissner to make an armored airplane.
By the time you came on the scene, grad school in the late 70s, here in 87.
By the time I got into school, there was a lot of funding in cloud physics. And in SUNY Albany, Vonnegut was a professor there at the time. Vince Schaefer had set up the whole program at Albany.
Kurt's brother was your professor?
Yeah.
You had classes from him?
Yeah, he was my advisor as a PhD.
He was your advisor, huh?
Yeah.
Vonnegut's brother. And Kurt Vonnegut put this in Cat's Cradle?
Well, in Cat's Cradle, there is a military scientist who develops a material that will cause water to freeze at room temperature.
Huh? So I'll go read Cat's Cradle.
And it's kind of the underlying theme is science runs amok. Once this guy gets this stuff out into the atmosphere, it just freezes up all the water on the Earth.
Well, don't give away the info from the end.
Well, well, see, at the time in the 40s, when Bernard was doing his work with silver iodide, Kurt worked for GE. He was a writer,
Really?
technical writer.
You don't say.
They both lived in Schenectady.
He and his brother were working for GE.
Yeah,
That's great.
I think Bernard got Kurt the job. But in any event,
So when you were in grad school, was this already fading as an issue?
no, it was going strong in the mid-70s, and the National Hail Research Experiment was going on, and there were some other. They had a big program in Florida.
So when you say cloud physics, is that the area in which WeatherMod is kind of cloud physics?
Well, you had to understand cloud physics to understand how cloud seeding would
Sure,
work.
sure.
And,
As opposed to cloud chemistry or cloud electricity or...
well,
I don't really understand how this field is divvied up.
yeah, cloud physics is more how little drops form into big drops,
Sure.
or freeze into ice. But in the early 70s, there was a Hail Research Experiment, which was terminated early because it was obvious things weren't working like they were hypothesized to. There was a Florida area cumulus experiment. They were trying to show they could increase rainfall in Florida
Right.
by seeding small thunderstorms, basically. And that ended in failure. They couldn't show any effect. And so by the mid to late 70s, science was not confirming that cloud seeding was the be-all and end-all that some people thought it was. And then I think it was the early Reagan administration, they just said, we're getting out of the business.
Of WeatherMod.
Research, federally funding research in
Right.
WeatherMod.
So by the time you got to IAS in 87, it was not a big issue.
There was one small program still running, and it was called the NOAA Federal State Cooperative Program in Weather Modification, and it was a write-in.
I'm sorry, what's a write-in?
Pork barrel.
Oh, what do we call that? A earmark.
Earmark.
But not here.
Well, we were involved in it.
Oh, you were involved in that. T28 flew
We-
penetrations for that project.
On a couple of projects.
It's called what again?
Federal State Cooperative Program in Weather Modification Research.
So
And that ended in the early 90s, 93, 94.
So 2 weeks from now, you're teaching Weather 101 at School of Mines. Bright kid raises her hand and says, Professor Detwiler, so does WeatherMod work? You say.
Oh,
Short answer.
We do, when I have taught our introductory class, we usually do at least one class. And the answer is it'll work in some limited circumstances. You can get some pretty consistent results. But those limited circumstances don't include thunderstorms.
Well, they don't. That's clear by now?
Well, it's unclear,
Oh,
I guess is what I mean.
it's not clear that they do. Is it a question of scale? Works on the small scale, not on the large scale?
Well, it's a question of complexity. In a very simple circulation, like what they call orographic clouds, where the wind blows up over a mountain and you get the cloud form.
Like the Black Hills.
Yeah, you get some orographic clouds in the Black Hills, but mainly I'm thinking more of like the Rockies and the Sierras.
Okay.
And the problem is that the air blows through. I mean, the clouds form and then drift over the mountain, and then the air comes down the other side of the mountain, and the clouds evaporate.
Right.
So there's a limited amount of time for precipitation to form and fall out. And if you can stimulate the process earlier and make it work faster, you can get more snow out of these orographic situations. And the trickiest problem is getting the seeding material into the right layer. But there have been some statistical analyses, some physical experiments, and it can work if you're careful about how you do it. But thunderstorms are so complicated that they go through. The circulations are less predictable, and thunderstorms kind of merge with each other.
So it's very hard to hit the target where you will have your intended effect. Is that fair to say?
It's very hard.
You can spend a lot of money and be unsure whether you made any benefit.
And you might have caused more hail,
Yeah.
as well as less hail.
Uh,
On the other side of that, physically dealing with the complexity and not being sure that what you're hypothesizing is happening really does happen. Paul Smith and Jim Miller and some others have done statistical analyses of hail damage and compared places where cloud seeding has been doing to neighboring locations where it hasn't been done, and shown a reduced hail damage in the areas that have been seeded.
They think a significant.
It's significant, and it's like a 40% decrease in damage.
So is the evidence for hail suppression better than the evidence for rain enhancement?
Well, statistically, they've also done studies of some of these orographic sorts of things and shown 5 to 10 to maybe 12% increases in seeded zones versus areas where no seeding occurs. But it's a question of philosophy of science, really. I mean, if you have a statistical result but you can't explain it physically, I mean, you might have some hand-waving explanation for how seeding material reduces hail damage, but you can't verify it. I mean, you don't have measurements of what's going on all the way through the storm.
You can track correlation but not causality. Is that fair to say?
Well, causality is a whole problem in itself, and philosophy of science, but just on a common sense term, I mean, science, if you have a statistical relationship but you don't understand physically how it works, scientists generally don't like that. They're uncomfortable with that situation. So that was the role of the T28, was to try to get some actual in situ measurements. Can we see the seeding material? Can we see where it goes? Can we see it having the effect that we think it has? And but hailstorms are like 10 kilometers across, 10, 15 kilometers deep, and you've got one little airplane flying back and forth measuring along some little pencil-thin track through the storm, and it just takes a long time to collect enough information to get those kinds of answers.
If you had some big Spanish Armada T28s, a big grid of them heading into a storm, would that be ideal?
Well, the original thunderstorm project, this is after the war, of World War II, they had this huge fleet of airplanes. They had nothing to do with them. And a lot of new meteorology was learned during the war, and a lot of questions came up. And so I'm not sure who funded it, but there was this thing called a thunderstorm project, and they ran 2 summers. One was in Florida, one was in Ohio. They had a fleet of these P-61s. They had 10 of them. And the goal was at least 5 of them would be working on any given day. I mean, that's how reliable this technology was in those days. And they had if you look at the report, their scheme was they'd have an airplane at 5,000 feet, 10,000 feet, 15, a stack of 5 of them
Stack. Yeah.
going back and forth through the storm.
And if you had a magic wand, would you set up a grid of 10 by 10 on 1 kilometer apart and send it through?
Well, that would be helpful. I mean, in a way, the polarimetric radar was kind of an answer to that problem because you can tell something about the shapes of the particles, at least the ones that are big enough to reflect microwaves.
Radar has improved, for sure. Research radar.
Research radars.
Has it reduced the need for in situ measurements like the T28?
Well, to some extent, it augments what you can get from the T28 because you get less quantitative information, but you get it over the whole volume of the storm.
Right.
There are some things that are important that the radars don't observe, and that is cloud water, supercooled cloud water. These little tiny droplets don't reflect.
So radar has not made aircraft measurements obsolete?
No.
No. Hey, in the big picture, what's the scientific significance of what was the scientific significance of the T28? What was it and how significant was it?
Well, I think its significance is probably mostly in the area of what you would call cloud physics or convective storm physics. Just verifying some of the hypotheses about how hail develops in a storm, how storms electrify, something a little bit about storm circulations, although it wasn't a terribly sophisticated platform for monitoring storm circulations. You could get some idea of the upward and downward motions, but not the horizontal motions.
But how did you know the upward and downward motions? By how it threw the plane around?
Yeah.
So by Charlie getting banged around in his harness, you could tell.
Well, you basically monitor the vertical motion of the airplane, and then Fred Kopp developed a very nice scheme for basically taking the aircraft equation of motion and inverting it. So if you actually know the vertical motion, what must the air have been doing?
Yeah.
And then a little bit of chemistry, but that we still, like I say, we haven't really finished analyzing that data due to lack of funding. So.
Well, Andy, thank you for all the information today. I enjoyed it. It's been very helpful.
Well, you've been very persistent. This is a long conversation.
Thanks a lot.